Okay, during my previous video we covered the Holts method, and during my previous lecture we did double smoothing, and then with double smoothing we tried to forecast like a line. Obviously, as we did double smoothing, forecasting the line was just like a horizontal line. And yes, I think we forecasted with an alpha equal to 0.2. So in this lecture, we are going to try to use the Holts method and to compare with what we did during the previous session. And later on, we will cover the Winta method, and finally an automated method that finds the best solution possible for a model. So let's go to my full desktop. So during the previous lecture, we covered this same code. The only thing that I have changed is the data set. Yes, because during the previous session, I did not found this data, the initial data. Yes, so we find the data since 1997 or something like that. So I already uploaded in Blackboard the data from 1991, and that is what we have after we double smooth this data set. Right, so let's do Control Enter very quickly. I will not explain this. If you want explanation on this, you need to see my previous video. All right, so this is the data set that we are doing now, yes. And so there is a few differences then, right? This is the data. This is the ridership time series. I'm telling R to do that. This is the differencing. This is the data after the differencing. Yes, I declare that a time series. I plan what is going to the validation period. Please see my previous videos on this. And then, yes, the video on this is partitions. So I think you can find something in R about partitions. So I do the partition for the training period. Please read about performance and evaluation if you do not know what is training period and validation period. I perform the partitions of both periods. One is around here, the second validation period is here, training period is before. And then, as you can see, I am going to conduct a forecast, or like, yes, with the command ETS, I am going to find a model with A and N. The first letter, this A, is for the error and is additive when you have A, and then nothing for the trend and nothing for the seasonal component in R. So we are just doing with an alpha equal to 0.2, and then we are making, like, this is the learning component that we covered during the lecture. Yes, and then we forecast with that model. Yes, this is the data for that forecast, right? We plot the data. As you can see here, we have the forecast already. It's a horizontal line. Yes, and then finally we do the fitted lines for our forecast, the fitted lines that we are using to forecast, and then we compare that with the validation period. This is our forecast with the validation period. And now we are going then to do something like more related to the session that we just covered. So this is the comparison of two simple exponential smoothing models. This one is without the alpha, so the alpha is going to be iterated and is going to be the optimum for the same model. So this is the Holts model, right? So I forecast this says opt with A and N. Yes, as you can see, there is not any alpha. I calculate the accuracy for the previous smoothing prediction that we did. Yes, and I calculate the accuracy for the current, the Holts prediction. Yes, so I use the Holts prediction versus the validation time series, this line here. And then, as you can see, I am able to choose which one of them has the best root being square root. Which one would you think is the best? Number one or number two? Yes, the right answer is this one. As you can see, the root mean square error is 82, is closer to 0 than 90. Yes, and if you see the other readings, I think you will find something similar. So that is why we've choose the optimal. I think you can see or double check that the second forecast, the Holts forecast, is actually more accurate. I think we are here in line 37. This is the Akaike criterion, yes. So everything is fine, and the smoothing parameters is here, right? Lines, so this is the Holts forecast in red. Yes, a little bit different from 0.2. This is the optimum one, and I think we finished there this model. Beyond that, we can calculate the model with an additive error, yes, and an additive trend. Yes, we can do that as well with the same model, but I think since this is very close to 0, we are going to get a very similar model. So let's do it. I'm going to control enter this. Same is exactly the same code that we did before. Yes, the only difference is this change in letter for additive trend. And as you can see, we have that the gray one is actually very similar, right? And we can calculate well, we calculated the accuracy here, yes. Would be great if you calculate the two best. Let's calculate this one just in order to get to know is the root mean square error is 82.82, and previously we have 82.82, so as you can see is the same one, yes, since we have this data that is very close to 0. Finally, we try multiplicative model with multiplicative error. Multiplicative error means that the error is fluctuating and suddenly becoming small, or is small and becoming large. That is multiplicative. I recall one of my first lectures on additive and multiplicative trends. So I ask you to come back to that one. And so that we have here for the error a multiplicative trend, and for the trend an additive trend. So let's see if this one works. The model is telling us that it cannot find an appropriate model for this data. Yes, so we can say that the error is for sure not multiplicative. Okay guys, so I cannot run this code, the multiplicative model, because the data is not allowing me. As you can see, actually there are parsing which it looks multiplicative, parsing which no, so I cannot tell that this data is multiplicative, guys, in the error. All right, I will see you in my next video where we are going to cover the rest theoretical part, the reminder.